The very first reaction that we are going to talk is hydrohalogenation. What is a hydrohalogenation? Hydrohalogenation is addition of hydrogen halides to alkene. Now this is an electrophilic addition reaction which is going to take place in two steps. The first step is the formation of carbocation, and in the second step is the formation of the actual product, which is alkyl halide in this case. When you have an alkene, we know that the double bond is the source of electrons, which means it's going to act as a nucleophile, right? And because this HBr has got partial positive and negative charges, so there's going to be a partial positive charge on the hydrogen and a negative charge on bromine because bromine is electronegative. The electrons from the double bond is going to go make a nucleophilic attack on this hydrogen, and the bond between hydrogen and Br is going to break. This is going to lead to the formation of carbocation. And once the carbocation is formed, the bromide ion is now going to act as a nucleophile, attacking the electropositive carbon, which is our carbocation here, to give the product, alkyl halide. There are two steps in this reaction, as we have said. So the first step is the formation of carbocation, which is a slow step. And the second step is the attack of the nucleophile on the carbocation, which is going to take place fast. Let's do the mechanism one more time. The electrons from the double bond is going to make a nucleophilic attack on the electropositive hydrogen, and this is going to break the bond between hydrogen and Br, and the electrons are going to go on to the Br to form the Br minus, and this will lead to the formation of carbocation. And once the carbocation is formed, the Br minus will make a nucleophilic attack on this carbon to give the alkyl halide, our product. Identify the products for the following reactions. Here is an alkene that is being reacted with HBr. So this reaction is basically hydrohalogenation reaction, which is an electrophilic addition reaction. What are the two steps involved in the electrophilic addition reaction? The electrons from the double bond is going to make a nucleophilic attack on this hydrogen, and the Br is going to leave. Right? This is going to create a carbocation. Now, which of these two carbons is going to grab the hydrogen? Now, because this is a symmetrical alkene, it hasn't got any preference where the hydrogen can go onto this carbon or it can go onto this carbon, right? If the hydrogen is going to go onto this carbon, then this would be the carbocation that will be formed. And if the hydrogen is going to go onto this carbon, then this is the carbocation that will be formed. But both of these carbocations are exactly one and the same, so there is no preference. So in the first step, we'll be creating a carbocation at the expense of a double bond, which is going to look like this. Remember, the carbocation is planar. Later, we'll talk about the stereochemistry of this reaction. Okay, so this is the carbocation that will be created. And the next step, the Br minus is going to make a nucleophilic attack on this carbocation to form the product. So this is a product which is an alkyl halide. Now let's go on to the next reaction. Here again you have a symmetrical alkene, right? If you want, you can put the hydrogens in here, right? There are two hydrogens in here, so you can put the you can start the electrophilic addition reaction. So the electrons from the double bond is going to go make a nucleophilic attack on this hydrogen, and the bond between H and I is going to break, and it's going to move towards I. And here again, there is no preference because this is a symmetrical alkene. If the hydrogen is going to go onto this carbon, then this is the carbon that will be having the positive charge and vice versa. Right? So let's write down the structure for carbocation. This is the carbocation that is formed. Remember, there is already one hydrogen that is existing in this molecule. So this is the already existing hydrogen. And on top of that, we have added another hydrogen. So this should have a total of two hydrogens now. And in the next step, the I minus is going to make a nucleophilic attack on this carbocation, forming the final product, which again is going to be an alkyl halide. When a symmetrical alkene undergoes an electrophilic addition reaction with HCl, it is only going to give us one product because it doesn't have any preference for the addition of the hydrogen. The hydrogen can go onto this carbon or it can go onto this carbon. Either way, it's going to give us only one product. But when you take an asymmetrical alkene or unsymmetrical alkene, then there's a chance that it can form more than one products and out of which one of the products can be formed in major quantity. Now here is one such reaction. This is an unsymmetrical alkene or asymmetrical alkene where you have different groups across the double bond. Right. When this alkene is subjected to hydrohalogenation, it's going to form two different products, but only one of these products is going to be formed in major quantity. Now, which one is going to be formed? For that, we have to look more into the details of the mechanism and also look into the different carbocations that will be formed. What is the first step in the electrophilic addition reaction? The electrons from the double bond is going to go and attack the electropositive hydrogen, and the bond between the hydrogen and chlorine is going to leave. The two carbons here are definitely different because it's an asymmetrical alkene, and we have labeled this as A and B. Now the hydrogen has the possibility to go get added to carbon A, in which case carbon B is going to have a positive charge. If the hydrogen is going to get added to carbon B, then our carbon A is going to have the positive charge. Right? Now let's write the two scenarios and also draw the two carbocations that will be formed here. When the hydrogen is added to carbon A, this is the carbocation that will be created. When the hydrogen is added to carbon B, then this will be the carbocation that will be created. Now, as you can see from the picture, from the carbocations, from the structure of the carbocations, the two carbocations are definitely different. This has a positive charge on a carbon, which has two hydrogens, whereas this one has got a positive charge on a carbon, which has got no hydrogens. Right? Now, in the next step, the Cl- is going to make a nucleophilic attack on this carbocation to form the product. So if the Cl- goes and attacks this carbocation, then it's going to lead to the formation of this product. And if the Cl- goes and attacks this carbocation, and it's going to lead to this product. Now, between these two, which one of these products are going to be formed? In order to answer this question, we have to look into the relative stabilities of the carbocations, where you can see that the tertiary carbocations are more stable compared to the secondary, and then comes the primary and then the methyl. Methyl cations are really unstable. Now, why should the tertiary carbocation be more stable? Just by looking at the structure, we can see that the tertiary carbocation has got many alkyl groups. So the stability can be related to the number of alkyl groups that a carbocation has. We can think that the alkyl groups are going to stabilize the carbocations by decreasing the concentration of the positive charge on the carbon. From the electrostatic potential map of the different carbocations, it's very clear that only in the tertiary carbocation, the positive charge on the carbon has been greatly reduced, and that is because of the presence of the alkyl group. How do the alkyl groups decrease the concentration of the positive charge on the carbon in the tertiary carbocation? This is because of one magic word called as hyperconjugation. Hyperconjugation is the overlap of the sigma orbitals with the empty p orbitals, where some of the electrons from the sigma orbital is going to move on to the empty p orbital. Okay, now let's see what's going to happen here when we compare the methyl cation with the ethyl cation. So in the methyl cation, there is no adjacent carbon-hydrogen bond, right? So this carbon is only attached to 3 hydrogens, right? So there is not an adjacent carbon in here. Let's look into the ethyl cation now. This is a carbocation, which is going to have the positive charge, and this is our empty p orbital. Now this carbon is attached to another carbon, which in turn is attached to 3 hydrogens. And each of these 3 hydrogens is attached by a sigma bond with the carbon. Right. Hyperconjugation is a process where some of the electrons from the filled orbital is going to move on to the p orbital. As more and more electrons are going to be moving onto the p orbital, what's going to happen is the positive charge on this carbon is going to be reduced. So this positive charge, which was once concentrated on this carbon alone, now going to be distributed onto the atoms which is losing those electrons. So in the case of ethyl cation, there are three such sigma bonds which can from which the electrons can move to the empty p orbital. In the case of isopropyl cation, there are 6 such bonds from which electrons can move. And in the case of tertiary butyl cation, there are 9 such bonds which has the ability to shift the electrons, thereby considerably reducing the positive charge on this carbon, and therefore the carbocation, the tertiary carbocation, is very, very stable. Let us now go back to our problem and identify which one is going to be the major product. So when the hydrogen has been added to the carbon A, then a primary carbocation has been obtained. So this is the primary carbocation. Whereas when the hydrogen has been added to B, it leads to the formation of a tertiary carbocation. Now between these two carbocations, which one is more stable? So we have a primary carbocation and we have a tertiary carbocation. Between these two, obviously the tertiary carbocation is more stable, and the product that comes from the tertiary carbocation is the one that's formed in major quantity. So this is a major product and this one is a minor product. Not always do we have to use the mechanism for the reaction in order to find the major and minor product for the electrophilic addition reaction of an asymmetrical alkene. We can also use Markovnikov's rule, but we have to use it with caution. Now, what does this rule say? The rule states that with the addition of a protic acid such as HCl, HBr, or HI to an asymmetrical alkene, the hydrogen is going to get added to the carbon which has the most number of hydrogens, and the halide ion is going to go to the other carbon, the carbon with more alkyl substituent. So this is how I remember M stands for most number of hydrogens. So now let's take a look at it. Without going through the mechanism, we should be able to find the product for this reaction. So according to Markovnikov's rule, the hydrogen is going to go to the carbon which has the most number of hydrogens. Between these two carbon, which one has got most number of hydrogens? Obviously, it is this one, right? So this is the carbon that has got the most number of hydrogens, and our hydrogen is going to go onto this carbon. We are going to add the hydrogen to this carbon, and the Cl is going to go onto the other carbon, and that would be our major product. So this is going to be our major product, and this would be a minor product. But keep in mind that you cannot apply Markovnikov's rule for every reaction, because there is a chance that major product that is predicted by the Markovnikov's rule is not the actual major product that you'll be getting in the reaction, because there could be possibility for carbocation rearrangements, which we'll be definitely covering in a later section. Using Markovnikov's rule, predict the major and minor products for the following reactions. What is Markovnikov's rule? Markovnikov's rule says that when you add a protic acid to an asymmetrical alkene, the hydrogen is going to get added to the carbon which has the most number of hydrogens. Now on this asymmetrical alkene, which one of these carbons has got higher number of hydrogens? This carbon has got 1 hydrogen, whereas this one has got 0, right? And therefore the hydrogen is going to get added to this carbon. And the iodide ion is going to go onto this carbon, right? So the major product is going to be this. This is a major product, and this one is the minor product. And you can also go through the mechanism. If you want to have this product, then it's going to lead to the formation of tertiary carbocation first. So it's going to lead to this carbocation first, and then the iodide ion is going to come and attack on this electrophilic carbon and form the product, right? So you can simply use the Markovnikov's rule to find the major product here. Let's go on to the next problem. This is a cycloalkene, substituted cycloalkene. So between these two carbons, which one is going to have more number of, which one has got more number of hydrogens? So if you want, you can show the hydrogens to see where the new hydrogen is going to go on to. This carbon has got 1 hydrogen, whereas this one has got none, right? Since it already has got 4 bonds. So this is the carbon which will be gaining a hydrogen. And with the addition of 1 more hydrogen, it's going to have 2 hydrogens here. Now, which one of these structures has got 2 hydrogens in here? Obviously, it is going to be this one. So the Br minus is going to go attack this carbon. This is going to be a major product. And this one is going to be a minor product. Regioselectivity. Here we are going to learn a new term in organic chemistry called as regioselectivity. What is a regioselective reaction? A regioselective reaction is a reaction where there is preferential formation of one constitutional isomer over another. A regioselective reaction could be completely regioselective, where there is 100% of one product that is formed, or it could be highly regioselective, where the major product is more than 90%, or it could be moderately regioselective, where one of the products is going to be about 75%, approximately 70%. Let's take a look into these three reactions and classify them based on their regioselectivity. So this first reaction is completely regioselective. Why? Because there is only one product that is obtained. Why should there be one product for this reaction? So if this product needs to be formed as the only product, then it needs to go through the formation of the tertiary carbocation, right? So tertiary carbocation is more stable compared to the primary carbocation that is formed here before it gives the product, right? So because of which this is the only product that is formed in this reaction, and therefore this reaction where it forms only one product is called as a completely regioselective reaction. And as you can see from here, these two products are constitutional isomers, wherein they have exactly the same number of carbons, hydrogens, and halogen, chlorine, but they have different connections. The atoms are connected in different ways. Right? So this is a completely regioselective reaction. Now let's take a look into this reaction, the second reaction. For the second reaction, one of the carbocations needs to be a tertiary carbocation. So this has to come from a tertiary carbocation. This product needs to come from a tertiary carbocation. And here it would be secondary carbocation. So between these two, which one is going to lead to the most major product? Obviously, it's going to be coming from the tertiary carbocation because it has got higher stability. Secondary carbocation, it is less stable, but although it is less stable, it is still going to produce some product, but that's going to be the minor product. Now let's go take a look into this reaction right here. So this reaction is a non-regioselective reaction. It's not a regioselective reaction because it has no preferential formation of any particular product. Both of these products are formed equally, right? Now why they are formed equally? Because each of these carbons has got equal number of hydrogens. There is one hydrogen here and one hydrogen here. So therefore it has the ability to form both of these products, and such a reaction is not a regioselective reaction. So while this is a moderately regioselective reaction, this one is a non-regioselective reaction. To summarize, electrophilic addition of a symmetrical alkene is going to give us only one product, whereas an asymmetrical alkene is going to give us more than one product, and it is a regioselective reaction, which means there is preferential formation of one regioisomer. And the stability of the carbocations is going to follow this order, where the tertiary is more stable compared to the secondary, primary, and methyl. And that is because of the hyperconjugation, which is basically the movement of the electrons from filled sigma orbital to empty p orbital.